you have two constraints, so two translation removed, and then you have one rotational degrees of freedom. But suppose if you want to constrain it completely in plane, then you need another constraint, so C3, so that this rotation can be eliminated. So the I think requirement is that the C3 should not pass through the center of instantaneous center of rotation, which is the intersection point of C1 and C2. So it should be away. There should be a perpendicular distance. So what we can say that when you extend the line C1, C2, and C3, they should enclose an area. And if you do that, you can fairly recognize that if this is the displacement from the center point, from the intersection point, then there will be always a moment, and that's when like C3 will constrain the rotation. So this is the requirement for exact constraint in plane. So 3 degrees of freedom in a plane, and 3 constraint can completely remove all the degrees of freedom in a plane. So that's we understood. And when those numbers, degree of freedom, so degree of freedom is equal to your constraints, number of constraints. You satisfy the condition of exactly constraint. Means there is no additional constraint, and therefore the number is whatever number is required is there. And we already discussed about what is the problem if it's over constraint, and that's why many times we talk about this exactly constraint design in precision design. So going further, I think what are the devices? Devices means what are the means? What are the different embodiments? So this is like concept, and this is how we can do. But how to achieve them? How to achieve exact constraint design? And so what we say when we talk about devices means what are the means, right? The mechanical connection to constrain one or more bodies degree of freedom, right? And then when we are talking about devices, yes, we are talking about links, contact points, or maybe like bar with articulating and connections, right? I think later we also realized that it can be also achieved through some flexures or compliant mechanisms. So this can be also added. So we say link, contact point, or bar with articulating end connections. Here we are mainly we depend on and we assume that these links are rigid and the motions are only at the contact points. But we can also use flexible elements called flexures in such a way that we get similar kind of performance. And that's the reason, like in this course also we'll be talking about those flexure designs. But I think the key concept is we should to define these constraint lines, and then we should be able to know what are the different devices or what are the different means, and then convert into flexure design, which may be needed when the motions range of motion are limited, and like in case of MEMS or NEMS, what it called micro electromechanical systems. So when we go at the micro level, we'll talk about flexures. So our role as a designer is designing the pattern of constraints. This is very important. Pattern of constraints that will properly constrain each part of a machine, leaving only those degrees of freedom that are desired. So you remove whatever degrees of freedom there and which is not required, you remove them by putting a good or a pattern of constraints. That's the idea. So in precision, in general machine design or in production, what you see that whenever we talk about precision or high accuracy, what we do is we tend to use double pins, right? So dowel pins, right? And we say, okay, this may work. And many times people, whenever you say, okay, how to get precision, they, okay, we'll put dowel pins and we'll achieve. But that's not true. And in terms of design principles. So what he is saying that pin and hole connection between bodies is a common constraint device in industries, right? So what we do, we have like this kind of symbol we usually encounter, right? And you say, okay, they are exactly placed, right? That's the assumption. But now, by now, you know that it's not possible. So suppose if you have a body and then there are two pins A and B. So in the given example here, what you see here is the so there is a pin, there are pins, and there are two holes, right? But because of the limitations, machining limitations, you know that it cannot happen. So there are three cases. Either the pin is smaller than the hole. So in this case, other cases when the pin is larger than the hole, so there will be interference. Here you have it can move freely, or exactly the same as the hole diameter, which not possible. But sometimes what you assume that okay, you drill the hole after the assembly and then you put the pin, but that is not a good practice. So what happens that what you can see here is this constraint, one pin to other pin. Actually, they constrain along the same line. And you know by now that the two constraints along the same line is over constraint design. So you don't get that accuracy or precision. You'll have a problem later because of the wear out and if there are any thermal issues that will lead to a lot of problems. So what is the way? So another principle many times we talk about is like instead of going for conformal like hole and pin design, what we talk about pin in V connection. And this is very important concept because many times in the industry, if we are talking precision, we talk about conformal surfaces, and actually that's the mistake because anything you want to support, you make a conformal surface matching exactly with that contact, and you know that it's not possible. There will be always some uncertainty. You cannot get a spherical surface, so a spherical ball sitting on a spherical hole. It's not possible. There will be always some uncertainty. So we always look for an ideal design. So what is the design which defines that surface? So theoretically, so in this case, suppose if you have a pin, V is good enough because V provides you that XY constraint. So if you have a V block, so this V block, and then you make a connection, then you know these are the constraint line passing through the center of. So this is the center of rotation, so it can rotate. And once you have this nesting force there, that makes sure that there is always contact made. And if that is achieved, actually you don't have any uncertainty. So how you do that? Actually, what you see in principle, there are three forces acting. Two are constraints, so C1, C2, and this is nesting force. So call it Fn or whatever. There is so don't call it Fn because many times Fn we say when there is a normal force. But yeah, it's a nesting force, and under these three forces, it will be under equilibrium and there will be no movement. So in design, if you have to do that, what you can do is, if you have what you can design, you can have a pin, and then you have this plate with this V connection. So if you have a V here, so what actually you are doing is there is a V here, bigger hole, and then you have a pin here. And what this bar is doing, if you think about this bar, is just a pin but then it's resting on the pin, and there is a small notch in this what you call it, this plate or whatever you call it. There is a notch here, so actually it bends here, and because of this thing, it acts as a spring. Actually it's nothing but it's like a spring. So initially it's like this, right, resting on those two bars and the two pins, and those two pins are like on the V, and now you just move it, you push it, so it takes this shape, and then here you have a stopper kind of thing, notch, right? So it stops. So by this, what you are doing is you're providing a nesting force, and there is a constant C1 and C2. So you can say C1, 2, and this is F nest, nesting force. And if you have this kind of arrangement, you can actually place this plate accurately with respect to these blocks. So pin in V is better than pin in hole. So in general, like many times we also worry like how to provide the nesting forces, right? So you want to establish the contacts, but how many nesting forces will be required? And many times you may need to calculate them. So for instance, in this example, so you have these two pins, right? And this bar is resting on them, right? So this is kind of reference, you can call it. And this is the floating body A, you call it, or not call it L, because you are already saying ABC. So what is, and these are the contact systems. So C1, C2, and C3. So you can see they are perpendicular to the surface and the contact, right? And so here you have the contact mix C1, C2, and C3, right? So at B, it's a perpendicular to the planes. So passing through this point, and then you have C1, passing through this point, and this is the normal, right? Normal direction. So these are three contacts, and as long as these contacts are made, they are in place. So body L with respect to the reference plane, or what you can say those two pins, it will be accurately placed, right? But you have to make sure that they are in contact all the time, because suppose if there is a movement, right, movement this way, so apply some force, or suppose you apply a force like this, there will be no contact, right? So it will move away. But as long as there is a force which so I'm just putting a random force, and placement is such that C1, C2, and C3 is always positive, then it works. So you need to find. So what you see in this figure, F1, F2, and F3 are the contact forces, right? So you agree. So you can always make a free body diagram, right? So equal and opposite, right? So F1, F2, F3, these are the forces required, and they should be positive, right? Positive all the time. So moment is a negative, it means there is no contact, right? In the other direction, it will not work. So where should be the force, so that that contact is always there? So one easy way is you can always have a conformal thing. So in the direction of F1, you have one force. In direction of F2, you can have one force. In the direction of F3, you can have a force, right? But there are too many then, whether you need those many. So this exercise is simply to illustrate that part, whether that is needed. So what you can always do is, okay, if you, so try to reduce, try to find the equivalence, right? So now moving towards B, what you realize against F3, just put F3, F1 and F2, if you combine, what happens? There will be a resultant force, right? So you can always have like F, so you can use the formula, right? F1, F2, and then you can always get F1, 2 here. So resultant force, right? So you can calculate. So you can say that, okay, if you apply force here, F12, passing through these points, actually, here you can replace F12. So F12 essentially ensures that you have a contact F1 and F2 there, right? And then if you have 3, now you move to F12, this C figure. So what happens then? You try to find the equivalence between F12 and F3, right? So you can always find some resultant force. How you do? You do the static balancing. So please do that. If you do that, you will be able to find the position of this. So F12 was here, and so I think very simple exercise, and you should be able to do that. I may ask this kind of questions now. So F12, and this is F3. So if you have F12 and F3, so this will be the resultant, and what will be the distance where it should be applied, right? A and B. So knowing that this is the overall distance between the two pins, so call it C. So C is equal to A plus B, right? So I think you can easily find it from force equilibrium. So please do that. So one problem can be formulated very easily. What is the, suppose what I want to have is F1, F2, and F3. They should be all equal, right? So what is the position and the magnitude of F1, 2, 3? So what you realize here, one force should be able to provide enough nesting force, and all the contacts can be made, right? There can be a question like what would be the disturbance force, right? So that, or inertia force when it's moving, then it may not work, right? Because if there is a dynamic force and acting in opposite direction, right? So moment any of them, F1, F2, or F3. So you can go backwards also and then find the components. I think you also realize that it also depends on this angle of B. What is the angle? So if you have this V, what is the angle? Whether it's a 60 degree, 90 degree. So I think for different cases, you can have a different result. So a simple problem can be easily formulated and it can work. Okay. So maybe as an exercise, what you can do is you can assume that with respect to this weight, C, right? And if I say whether it's a 60 degree or 90 degree, so two V groups, you can think of one. In one you have 60 degree, in one you have 90 degree. You can even think of 120 degree, right? So if you have this kind of different angles, whether this point F1, 2, 3, the magnitude. So F1, 2, 3, I would say, I'll say F net, right? F net or F nest, right? Try to find the magnitude, and what will be the relationship between this A, B, and C, right? A, B, and C. So just do that, and I may ask a question either in tests or in quizzes or in other platform. So I hope it's clear. So this is the calculation, and then what will be the location and where should be the nesting force. What is the point of application? So this is these are the different means how to achieve them. So this is you found that, okay, what is the magnitude, what is the line of force, right? Those kind of things you can get from here, right? But how to achieve them? So there are various means. Of course, if you have eccentric weight, so weight itself, weight of this bar can give you, so this is now weight mg, right? This can also provide you the enough nesting force. In many of the design, you have these eccentric cams. You can either weight or you can also say eccentric weight. So you can put additional weight to achieve that. Eccentric cam is like you have point of rotation. So you have a pin, but then you can have is something like one side bigger than the other, right? So here radius and here radius are different. Huh? So moment you turn it, you will start squeezing it. So this design is many times used in bicycles to quickly remove your tires or wheels from this, or even your seat. So if you have any bicycle, you can look at it. There are many designs doing that. So wherever you need some force quickly, I think you have this eccentric cab and then mostly connected with some kind of lever, right? Lever, so that you apply a force, you can easily lock and unlock it. So this is one possibility. Another is you just put a spring. So along that point, so because of this spring force also, you should be able to provide that. Other is like you have this kind of threaded thing here, and then you just screw it. So you turn it, and then you can move along this direction. And you can also get required F123. So I think there are various ways, and depending on the application you choose, right? And many times this is preferable. So not necessarily you have to always use this kind of spring. There are various designs, so you can have like you can use even flexures, right? So if you have this thing and suppose you have this one contact at this point, you can have something placed also and then just lock it. Right? And you can have some way to also load it here so that it presses here. So there are various ways, and you can have your own. You can be creative, and you can find your own ways to provide these nesting forces. You have to also find this window, like the forces. Like here, a very simple case, so you can find that what will be the direction of the force, but yeah, but suppose if you have to find what are the possibilities, right? What is the window? Then I think we have to go through this exercise. And here, what we are talking about C1, C2, C3 contacts, and what we want to have is contact for there is always some contact made. So if you take a pair, so C1 and C2, there is a instantaneous center of rotation, which you call it IC12. Similarly, if you take C2 and C3, it can rotate along this point. If you have C1 and C3, you can have an instantaneous center of rotation here. So, right, there are three instantaneous of center of rotation, and you have three constraint lines. So, what will happen? So, it's just an illustration that if body is moving along this line, actually, you lose this contact. So, there is no contact along this. No contact established, right? If you have this thing and it rotates along this way, you lose this contact, right? So you can likewise go to C1, C2, C3. So what is the requirement? So suppose you want to have these connections made, you need to have a force acting or moment acting along this direction. To have moment acting. So here, if you see, but you realize that if you are applying a force, then you have to ensure that there is a resultant moment. Like if you are, I'm talking about C12, there should be a moment acting along this direction, so that there is always contact made at the other contact, right? The C3. If I'm talking about C23, there should be a moment, resultant moment, which allows this contact, right? There should be some contact. And if I'm talking about C13, there should be a resultant moment acting in this direction, so that this is. So any force we are talking about, that should ensure all these three, right? Then only it will work, right? So the way to look at it is, suppose if you take a random force, this nesting force or external force F, what will happen? Whether it should be able to work, right? And the easy way to look at it is, if so, with respect to the force, you have to also realize that it's not just the magnitude; it's also the line of action. The point of application is equally important, because you have to also talk about the moments. So if this is the force and this is the line of action, what will happen if you talk about this point? Because of this force, there will be moment established, which is requirement, right? If you go back, I think this is what we want, right? There will be a moment along this direction, because there is a moment arm. So from this point, there is always a moment arm, right? So there is a positive moment along this direction. Similarly, from here, if you talk about, there is a moment arm. So you can say there is a positive. But if you take at this point, what happens, since it's passing through this side, actually there is a moment arm acting along this direction, right? Which contradicts with this one, this requirement. It means this is not possible. Now, if you do this, this will fail here. So similarly, if we do, like, there are various options. So, right, whether this force is good, whether this force is good, right? So what we find that if these lines, so we will be able to define this bold lines. uh, and what we realize, that if the force is somehow passing through this area, it will not achieve uh, nesting force with a single force. This is not possible. Mind that we are not considering the friction part yet. Friction is not there. Still, we have a very limited scope. So moment it passes through, so this is valid option, this is valid option. But moment it goes like this will not work. Moment it goes like this will not work, right? Moment it goes like this will not work. So this is very nice exercise, and you can try yourself. So I'll upload the slides later and you can check yourself. So I think it's about 10:30. Whether we should stop here. So I'll just stop here for some time and quickly come back to you. Yes, so just switch on your mic and let me know if whether this is going in the right direction, whether you are able to digest it. Please. So Mayank, I think you have a problem with your mic. So did you fix it? I would like to know. Mayank? What about Jishnu? C1, C2, and C3. Imagine these are the contacts, constant lines, right? So along this, if the contacts are made properly, if these contacts are always there, C1, C2, and C3 between these two bodies, along those lines, it cannot rotate, right? It cannot move. So what happens? Previously, we talked about the two constraints. So imagine if you take C1 and C2 only. These constraints are there, and just assume that C3 is not there. It's not there. So what will happen if you try to move? So if C1 and C2 is there, you also know that there will be a center of rotation. So at this point, so if you just extend these lines, right? C1 and C2. So you find a intersection, right? So this is the intersection and perpendicular to the plane. So the axis passing through this point and perpendicular to the plane, it can rotate, right? I think this is what we discussed earlier when we are talking about this. So you have to, so one by one, you talk about two constants at a time. So when you have C1 and C2, and you extend these constant lines, right? There is intersection here, and there is a axis perpendicular to the plane, and passing through this point, this body can rotate. And why this is possible? Because in order to have a motion along this, if this is the contact, C1 and C2, these are the constant lines, the contact probably on the surface, right? So at the contact point perpendicular to this surface, at this constant line, you have a motion like this, right? So if you try to rotate along this axis, this point will try to move along these directions, right? Which is possible instantaneously. So what we are talking about is for the instantaneous motion. And that's the reason we say that it has a one rotational degrees of freedom. And what we can say that this is also your instantaneous center of rotation. So we are using the same principle to study this one. So if you take just C1 and C2, we have this. Similarly, if we take C2 and C3, so when we are talking about C2, C3, you just assume that C1 is not there. So if we are talking about C2 and C3, then this can rotate at this point. So perpendicular to the axis, perpendicular to the plane passing through this point. Similarly, with the 1 and 3. So if we take 1 and 3, this is the IC, instantaneous center of rotation. So these three are defined, right? Once these three are defined, what is the scenario in which it can rotate or lose the contact, right? So in this case, right, if I'm talking about only C1 and C2, and if there is a force, any disturbance or any force, right, acting, so either this force or this moment, so at this point, actually, what it does, whether it's F or M, you have a moment acting along this direction, right? And because of that, the contact here is no more, right? So in order to have this contact made all the time, what you need is you need to have force or moment, equivalent moment at this point all the time. Then only you can have this contact made. So what is important is this one will, this is not good, this is good. This is what you want. That there is always contact established here, right? So that's what you see here. So C12, I C12, you need to have moment here, so that this contact is established. Similarly, so similarly, if you talk about IC23, so what happens if it goes, if you have a moment this way, so if you are, so moment at this point, right? So if you are talking about this moment, this will try to, there will be no contact here, so this is not acceptable. Okay. What is acceptable is this moment. So this one will moment bring this towards this, right? So you will have contact as established. So that's why you have this moment. So we are talking about the requirement. What is the requirement? What should be the means how this force should apply or the moment should apply on this body, so that you always have a contact made. Similarly, because body can rotate at different points, right? Because you have the instantaneous center of rotation. So you have to make sure that these contacts are, so you are talking about now three moments. So whenever you have a force or moment acting on this, it should ensure that the resultant moment, effective moment at various ICs, instantaneous center of rotations, it will be in this way. What do you realize means I can ask a question here, right? Is it possible to have one moment here which can constrain or provide the enough nesting force? Any of you? Is it possible? If anybody can speak up. But see, the moment anywhere, suppose if you take a body, right? And suppose if you apply a moment at this point, actually it's the same moment everywhere, actually, right? That's the basis, right? For force, it's a different. So suppose if you apply a force, and if you take this point, this point, this point, this point, equivalent moment will be very different because it's not just F, but moment arm. Also talking about this moment arm. So in this case, if you apply a moment, suppose external moment acting along this direction, what will happen? M external, I would say. This is established, right? This is in clockwise direction. This is clockwise. This is counterclockwise. So this is not established. This is also counterclockwise. So if this is the case, so one is clockwise, the other two are counterclockwise, you cannot have one moment. So it means with one moment you cannot provide all the nesting forces required, right? So I think we move forward, and so this is the requirement, and based on that, you just try to find okay, what are the feasible region. And this is one example, like if you take any F passing through, so these are like kind of windows. So if you just connect this IC and if it passes through, yeah, I can hear some noise. So can you just mute your mic? So what happens? It will not work. Similarly, like so, we'll come again when we talk about the function. So again, you like connect these things. So and then try to find what are the feasible regions. So you realize that actually these are the regions. So it can extend. So if it passes through this, it will not work. And similarly, this is also not feasible. So you can check yourself. So suppose if I say, okay, oh sorry, whether if you have this force acting, whether you will get a nesting force, required and nesting force, right? So you can talk in terms of the what is required, right? So we'll come again, I think, with some examples, and you will be able to appreciate or understand. Okay. So moving ahead, I think quickly you finish few slides and then we can start. So it's just about the application part. So suppose if you have this two parts A and B, and suppose you want to have this distance between this top and bottom surface, particular value. So what is saying? Precision of position, also called repeatability, is the degree to which a part or feature on a part will return to exactly the same position time after time. So every time you do, you get the same value. That's the repeatability, and that's the precision. So when a machine is designed so that its parts are exactly constrained, extraordinary precision is automatically obtained. So if you follow this principle, what it says that you can achieve precision automatically. That's the idea. So talking about the accuracy, also the degree to which the location of a part or feature exactly coincides with desired or intended location, right? So how far you are from the intended location or desired location. So what is saying? Precision is achievable without accuracy, right? Without accuracy, but accuracy is not achievable without precision. When we say precision, we talk about the repeatability. That's a very important. Okay. So what it says, precision is achievable without precision, even if it's not very accurate, you still can achieve precision, high repeatability, but accuracy you cannot achieve without precision. And that's the difference. And by designing exactly constant connection, we can achieve high precision machines using ordinary, low cost, inaccurate parts. This is very important because this is something contradictory to general belief, right? Most of the people think if you're talking about high precision machine, you need very high precision parts, but that's not true. What he's saying is if we follow these principles, like the constant connections and avoid over constraint, we can achieve high precision machine using ordinary low cost inaccurate parts. How? So this is one. The next stage is then through the use of adjustment and fixturing techniques, accuracy can be achieved. Okay. So the first part will give you precision, that is repeatability. And accuracy you achieve through adjustments and these techniques, right? Okay. So this is very good example. What you want that this distance d, in this case, suppose you have a case where A and P should be assembled, A and B should be assembled, so that this D is achieved, right? And suppose in this case, okay, it's one gauge two, so whatever, this is your gauge, and suppose you want to have that. So what has been done is, with the three contacts, you can get an exact constraint design, right? So you have C1, C2, and C3. What is the difference you see here? So we are talking about this case, right? Exactly constraint, right? And with the exactly constraint, we will achieve repeatability. So every time we do, what is the extra thing done here? This slope. And this slope is basically for adjustment. So what it does is, these three contacts, exactly the way it's designed, you can achieve exactly constraint design. It means you can get high repeatability. But providing this slope also ensure that this C can be moved. So depending on the kind of adjustment you want at this point, what you can always do is, suppose you assemble and then you are not happy, you find that there is either it's a small or big, you just adjust with some kind of screws. So you can slide this block C along this ramp or slope, and you can accurately get, and then you can lock it. So once it's locked, you will achieve the same position every time, right? Other way is, suppose you don't have a slope, and this is the thing you have in the other embodiment. So suppose you know how much is missing, right? If you know this inaccuracy, right? So you just choose a seam of that dimension, right? So suppose it's 0.001, right? You take a seam of 0.001 and then assemble it. You will get it, right? So every time you do, you get the same thing. So this is how. So it means you don't need to have very accurately machined parts A and B, but using the same concept. So here you use this concept, and what it says, you use ordinary low-cost inaccurate parts, increase the repeatability, and then providing some adjustment, you achieve the accuracy also, right? And that's what you are doing here. So with the exact constraint design, you achieve the repeatability, and with the way to adjust, if you provide a way to adjustment later, you'll be able to achieve accuracies as well. I think that's the fundamental, and that's the very basic principle in designing any precision equipments or machines. So one of the example is here. What you also do is you can make this C1, C2, C3 adjustable. So suppose if you have a camera, and suppose if you have this CCD sensor to place it accurately, what you do, you just use C1. Usually, if you don't know about this, what you do, you try to get a a slot and try to put it here, and somehow with the 4 screws you try to put it there, but you can't. Suppose if I'm talking about micrometers now, you cannot do that. So best way is, okay, you in a plane, suppose if you have a surface, you place this linear CCD sensor and then you start adjusting with C1, C2, C3. And this is the embodiment. So when you start rotating these screws, actually you are adjusting it. So with the 3 contacts, what you did, you got the exact constant design, and once done, this is the way to adjust. So you turn it and adjust it and lock it. That's it. And this is very simple example to show that how it can be achieved with very normal components, right? Ordinary components. So I think this is where we stop today.